Hey guys, this is Carrie, and in this video we're going to be doing lesson 11 on trig waves day 2. So it's been a while since we've had a lesson, but where we left off we were talking about two different ways of measuring angles. So the same way that there's two ways to measure distance, I don't know, like feet or kilometers, there are two ways to measure angles, and those happen to be radians and degrees. Now it's really useful because we're such pros with degrees to be able to convert radian measurements into degrees so that they're easier to work with. So the most important fact about radians, well, debatably the most important fact about radians is that a full circle is 2 pi radians. We also know that a full circle angle would be 360 degrees. So we can use this fact to convert all of these. So 2 pi radians would be 360 degrees because this is a full circle. If 2 pi radians is a full circle, then pi radians would be half of that, right? So this would be a semicircle, 180 degrees, or a straight angle. And this is the fact that now we transition to using most of the time. So whenever we see pi radians, for example, here when we see pi radians, we know that pi radians is 180 degrees. So we divide that by 6, and that will give us 30 degrees if we use our calculator. Here we have 9 pi over 5, so we can go, well, pi radians, that's 180 degrees. This is 9 times 180 degrees divided by 5. $324 degrees. Cool. So where this comes up quite a bit is when we want to find the sine, cosine, tangent, etc. of these trig functions. Here it says determine the exact value. So exact value is a keyword that the Regents uses to mean not a decimal. Because oftentimes the decimals, what you have to do is you have to cut it off somewhere, and then it would no longer be exact. So we want our answer here as a fraction, or square root. Okay, so cosine of 5 pi over 6. Oh man, how do we do this one? Well, my brain still doesn't think in radians, especially with that long week off from new lessons. So let's convert this one to degrees. So it's going to be cosine of 5 times pi radians, just like before, is 180 degrees, all divided by 6. We can do this piece that's in the parentheses here. I'll box it in blue. Let's do that part on our calculator. $150 degrees. Okay, now this is a problem we know how to handle. So in order to figure this one out, we need to have a graph of 150 degrees. So we think about a 150 degree angle that's going to start on the positive x-axis. That's going to rotate upwards. So starting here, this is 0 degrees. This would be 90 degrees. This would be 180 degrees if we rotate it all the way to there. Another 90 would make this 270 degrees, and another 90 would make that a full circle, 360 degrees. So to get 150 degrees, that's going to be somewhere between 90 and 180. So let's graph that here. All right, now if we want to find the cosine of this angle, we have a variety of strategies, right? When we first learned sine, cosine, and tangent, we were looking at those right triangle cases. And we had so, ka, toa. Now clearly 150 degrees is too big to be an angle in a right triangle. It's like this obtuse angle that you're looking at right here. So this method is out. Then what we saw is that it was helpful sometimes to think about the coordinate plane definition. So if we looked at the same triangle, we saw that this would be the radius out to the point. And then graphing the point, this would be the x coordinate, this would be the y coordinate. And so our trig formulas, opposite over hypotenuse, became opposite over hypotenuse, y over r. Cosine was adjacent over hypotenuse, x over r. Tangent was opposite over adjacent, so y over x. Now, none of these formulas are useful either, because even though these work for big angles in the coordinate plane, we don't know the x, y, or r value for this angle, so that's out. So our final method is to use a reference angle. And the reference angle, since we haven't talked about it in a long time, we usually write it as alpha. And alpha is always the positive acute angle between the terminal side and the x-axis. So you have two choices. Either this one is alpha or this one is alpha. Because alpha is always an acute angle, we know that this one right here, this has to be alpha. All right, now from the diagram, we can tell that alpha and 150 degrees together make 180 degrees because they make that semicircle straight angle. So if we wanted to solve for alpha, we'd have to subtract off the 150 degrees, and that would give us that alpha was 30 degrees. It takes a second to mentally verify here, but if alpha is 30 degrees and this is 150, yeah, that is definitely 180 degrees. All right, so how do we use alpha? Well, we discovered when we were talking about reference angles that the cosine of the large angle, 150 degrees, is almost the same thing as the cosine of the reference angle, cosine of 30 degrees. Now, where this is advantageous is for the cosine of 30 degrees, we know that. We have a special triangle called the 30, 60, 90 triangle. 30, 60, 90, 1, 2, square root of 3. And so if we do the cosine of 30 degrees, that would be adjacent over hypotenuse, square root of 3 over 2. And the last thing to think about if we want these to be exactly equal is to do our all students take calculus. Only sine is positive in this quadrant, so our cosine value has to be negative. All right, that's our final answer for this problem. So you didn't have to show all of this work if you knew right away it was the reference angle, but I find especially after a long break that it's helpful to re-go through that process of all of the things we know and to show why we have to use certain formulas. All right, so where this pushed us was in this interesting direction about something called a trig wave. So if we think about an angle in the coordinate plane, the sine of that angle is going to start off with some value. And as that angle opens up, the sine is going to change because the angle is changing. But after we return back, after one full circle, all of the sine, I'm using this version of sine, all of the sine values are going to start to repeat because the angle repeats on itself. And then again they're going to repeat. And then again they're going to repeat. And then again they're going to repeat. And forever, if we keep changing theta, if we keep opening that angle up further and further, the sine values are going to keep repeating each full circle. And a full circle is 360 degrees, but we like to think in radians now, so that would be 2 pi. So to avoid going through the derivation and redoing the lesson from last time, you're welcome to re-watch the lesson from last time. What's important with trig waves is that we're supposed to draw one period, and we'll talk about what that is in a second for each of these. Now for a sine wave, because it starts to repeat at 2 pi, we can put 2 pi on our graph. And we know that whatever we have here, don't draw this guys, so whatever we have here, it's going to repeat here because we have the exact same circle. But that's not what we have there. For sine waves, what we have is sine always starts at 0, 0. So we start at 0, 0, and sine waves go up, they come down, and then they go back up. And that would be one period of the sine wave. Now, the sine wave, as we showed here with the circle, it does repeat forever, but it's not very interesting because each full circle just does another copy of that graph. So oftentimes, we just draw one cycle of it. Now, it's key here, they said make sure to label the 5 key values on the x-axis using radians. So we've got one key value. This one is 0, of course, because 0 is 0. Halfway in between is going to be where it hits the x-axis. This is pi radians. And then it's really interesting. Halfway in between that is where it hits its maximum height, which would be 1. We proved this last time, so this is feeling like, oh my god, I don't remember this. Rewatch lesson 10. So between 0 and pi, this would be half of pi, pi over 2. And then here, at the minimum value, which would be -1 on the y-axis, this is 1, 2, 3, 3 pi over 2. All right, now cosine's graph is really similar. The same way sine repeated, cosine is going to repeat. So we can make our 2 pi marker. That's going to be one full cycle, and then cosine will start to repeat. But instead of starting at 0, 0, cosine starts at its maximum height of 1. So this one starts off at 1, and then from 1, we go down. Oop, that's not a very good graph. We go down, and we come back up, and then here it finishes. And this one I always find a little harder to draw, but we can see that it's ready to start repeating itself, right? Because if we were to continue on, it would have that exact same shape, and then again, that exact same shape. So each time through a full circle will give us a full section. Now, these sections are called periods, and that's an important vocabulary word for all of the future lessons. So let me mark it on the diagram. This would be one period, one cycle of the graph. This would be one period of the cosine graph. And we're only assigned to draw one period. All right, so similarly, all of the important stuff happens at these key values. So halfway in between 0 and 2 pi, that would be pi. Here, I didn't draw it very well, right? This should be where it hits 0. This should be halfway in between 0 and pi. This is pi over 2. So where it hits 0 is very important. Here where it hits 0, this should be halfway in between these two. And that's 1, 2, 3, 3 pi over 2. And these values will always be the same for the basic sine and cosine graph. Now it's hard to draw these things exactly though. All right, so let's see. Just to confirm that we've got the 5 key values on our x-axis. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And these will always be your key values for sine and cosine basic graphs. All right, so the graph below shows the sine wave. How many periods of the sine wave are shown below? Well, periods are full cycles. So here we go. 1 and done. 1 and done. 1 and done. So each cycle captures this behavior of a maximum, a minimum, back home. A maximum, a minimum, back home. A maximum, a minimum, back home. And so using the colors here, it looks like we have a green cycle, a red cycle, and a pink cycle. So 3 periods. All right, now see if you guys can do the same thing with this cosine wave. All right, so a natural question you might be asking is, well, what are waves good for? And it turns out that waves come up all of the time in phenomena that we experience in the world. So in the last unit, we spent a long time with exponential functions, and we modeled things like population growth and how bank accounts grow. We looked at 7% interest rates and what that would do to our retirement accounts. Another great example for exponential functions that's actually pretty relevant as you've been reading the news is the spread of a virus. And it didn't quite line up with our study of exponential functions, but I remember reading a lot of headlines about things like doubling every 3 days in the spread. And that would give us, from the last test, that would definitely give us an exponential function where the number of infected people was going, or number of people that had the disease was going up exponentially. Now, it's a little less tied into current events and a little less dark, which is kind of nice to take a break from the news. But some natural phenomena that can be modeled with sine and cosine waves are actually anything that repeats in nature, we model, or we represent as mathematicians, we represent with sine and cosine waves. So if you think about anything that repeats in nature, solar cycles, hours of daylight, that's not a good one, that's boring. Waves like at the beach, when you're surfing. What else repeats in nature? Oh my gosh, so many things. Let's see, like a pendulum back and forth for a clock. A bouncing ball. Anything that repeats, we use sine and cosine waves to model. But my favorite example, actually, is sound waves. And I'm super sad not to do this lesson in person because I love to bring in my guitar and actually play some guitar and talk about how the math ties in with the sound waves that are coming out of the guitar. But if you think about a guitar string, right, when you pluck a guitar string, it's going to start to like oscillate back and forth, start to wave back and forth. And that wave creates a sound wave that causes your eardrum to vibrate. And all of those things, the guitar string, the sound, or the air vibrating, the eardrum vibrating, all of those things are repeated phenomena in nature. And so they're all modeled using sine and cosine waves. Now, I like to play electric guitar. So there's like a lot of ways you can change those sound waves. And when you change those sound waves, you're actually changing the math behind the wave. So if you think about amplitude, sonically, like as a sound, that's how loud the wave is. And so if you think about your normal sine wave, let's say you play a sine wave. Your normal sine wave, 1, -1, 2 pi, 0. What do you think you'd have to do to make it louder? Well, it turns out that what you do to make it louder is you just make the amplitude higher. And the amplitude is how high or how low the waves go. So if you want to make a really loud wave like, "Hey guys, this is Carrie!" then what you're really doing is you're just making the wave taller and shallower. And it's always symmetric like that. So the amplitude is how tall the wave is. And the taller the wave is, the more your eardrum will vibrate and the louder it sounds. All right, now this isn't the only way that you can change the sound of a guitar string. So I don't know how many of you guys play guitar, but you have the period of the wave, 2 pi, and you could imagine that you could shorten that period and maybe make it pi instead, so that it did 2 periods inside of that interval. Or maybe you could make it really fast, like a really fast I don't want to use pink here. Whoa. Oh no. Really? Okay, cool. Like a really fast vibration here. And maybe it will be like vibrating a lot of times in a short interval, or oscillating back and forth a lot of times in a short interval. And this is actually really good to show on a guitar, because what you're doing when you shorten the period of the sound is you're actually shortening the string by putting your finger down on the guitar. And so if you play guitar, you know that when you put your finger down on the guitar and you shorten the string so that only this part of it is oscillating, what it will do is it'll actually play a higher note. So it's not a louder note, it's a higher pitch note. So changing the period changes the pitch. And so a silly example of this, right, is if you want to talk in a really low voice, like, "Hey guys, this is Carrie," you'd be talking with a really long period because it has a really low pitch. And if you wanted to talk in like a Mickey Mouse voice, like, "Hey guys, this is Carrie," then what you would be doing is you'd be talking with a really high-pitched voice, and so the period of that voice would be really short. Now finally, this is the most interesting, and also, for me, the most interesting. I mean, we'll all Well, I'll decide for ourselves. But whenever you hear someone's voice, oftentimes you can recognize that it's like Carrie's voice. I think I have a really distinctive voice, and you guys probably have really distinctive voices as well. And also you'll notice that different instruments, even when they play the same note, like a piano playing a C and a guitar playing a C, you can tell which one is the piano and which one is the guitar. So the quality of the sound, which is independent of the loudness and also independent of the note that you're playing, it's kind of like the uniqueness of your voice or my voice, or the uniqueness of a guitar against versus a piano. That's actually based on the shape of the wave. So a normal sine wave is shaped like this. But it turns out that when you play an instrument, the wave that comes out can sometimes have a square type shape, or it could have a totally different shape. I don't know, it's hard to draw these. It could have a totally different shape, and you probably have seen examples of this before in just your life talking about sound. And each of these would sound different. So how do you change the shape of a sine wave or a cosine wave? And that's a question that's a little bit outside the scope of this class. The way you change the shape is, instead of just using one sine function or cosine function, you add together a bunch of them. And by adding up like a sine of x plus a sine of 2x plus a sine of 3x, you can change the shape of the wave so it looks like however you want it to look. And that is like how you change the sound of an instrument. So a lot of computer programs do this. If you do any like making beats on your own, or like making songs on your own using computer generated sounds, those sounds are generated by constructing a wave out of mathematical functions. All right, so let's talk math now. State the amplitude and period of the wave graph below. Determine the equation of the wave shown below. All right, so amplitude, that's how loud it is. So this one goes up to 3. So amplitude is always a positive number. So it goes up 3, down 3. So the size of the wave, the size of the vibration, the oscillation of this wave is up 3, down 3. So the amplitude is 3. The period, and the period isn't going to be very exciting today because we're going to talk more about the periods of graphs on our next class tomorrow. But the period of this wave, one full cycle, takes 2 pi to repeat, and then it would keep repeating. All right, so the way we construct these equations is a basic sine wave has equation y equals sine x. So our new version for this one is going to be the same equation, but because it has to go 3 times as loud, we just put, no, go away thing, I don't know how to, we just put y equals 3 times the sine of x because it goes 3 times as loud. Now, we knew this one was a sine function because it started at 0, 0. If it had started at its maximum, it would have been cosine. State the amplitude and period of the graph shown below. All right, well this one, it's a sine function because it starts at 0, 0. The amplitude is it goes down 4 and up 4. So the size of the vibration here for the amplitude is 4. And even though it goes down 4 first, it's still positive 4 for the amplitude. The period, let's see, it has to go down, up, down. Okay, yeah, so it does 1 period in 2 pi. This is one cycle for it because it goes down and up, and then it's going to go down and up again. All right, so putting this in our equation, the only thing that's going to change is because the amplitude was 4, we have to have 4 times whatever the regular sine of x would have been. Now, this one is weird though. It's actually like an upside down version of the regular sine graph. The regular sine graph goes up and then down. This one goes down and then up. So to flip it, you make the whole equation negative. And now you've got your equation. All right, state the amplitude and period of the graph, of the wave graph below. All right, this one's a sneaky one. Well, right away we can tell it does not start at 0, 0. It starts off at 8, which is the maximum value. So this is going to be a cosine graph. All right, so the amplitude The vibration size here is it goes up 8, down 8, up 8, down 8. So the amplitude is 8, which means we'll have to have an 8 in front. The period, oh, this is the sneaky part. All right, so I don't know if you saw this, but the period, it starts at its maximum, goes all the way down, all the way up to its maximum. This is one period right here. And they were really tricky in this question. They put a second period here because it repeats the same thing. So one period is 2 pi. And we don't have to worry about that because 2 pi is the normal period for cosine, so nothing has to change in our equation. So you should find today that all of the periods are 2 pi. Now I scrolled up here because if we look at our cosine graph, this starts at our maximum, goes down, and then goes back up. This one starts at the maximum, goes down, and then goes all the way back up. It exhibits the same pattern. So we don't need to flip it. We don't need to put a negative sign there because it has the exact same shape as a regular cosine graph. All right. So guys, that's the end of today's lesson. You're going to be stating the amplitude and period for a bunch of these waves and writing their equations. Please do both parts, the amplitude and period and the equation. You should find that the period for all of the waves in today's class is 2 pi, but just explore that and make sure that you confirm that. And next class we'll talk about what changes in the equation when the period is not 2 pi. All right, so I wanted to show you a couple examples of the ones here that we didn't get a chance to talk about. So for problem 6, hopefully you've given this one a shot on your own. And for problem 8, we'll also talk about this one. So for problem 6, on the grid below, draw one period of the graph of the function y equals 5 sine x. Because it's sine, it has to start off at 0, 0. Sine goes up and then comes down. And wait, let's confirm that. It is positive, so it does have the normal behavior. It's not flipped. Usually sine goes up to 1, but our amplitude here is 5. So this is going to go up 5, down 5. And so because the size of these oscillations is up 5, down 5, the amplitude is 5. And then lastly, we have to label all of the key values on the x and y axis. So we've got 5, negative 5, we've got 0. The period is 2 pi, which is one full circle or one full cycle of our graph. Halfway through would be pi. Halfway that would be pi divided by 2, because that's half of pi. And then this would be 1, 2, 3 pi over 2. All right, so we've got everything labeled full credit graph here. Now, you can't really use your graphing calculator to graph these because it doesn't plug in the nice values for you. You want to make sure that you're plugging in 2 pi, and your graphing calculator won't plug in 6.28 or the decimal version of this automatically. All right, so with this one, be careful because it's negative. Think about how that's going to change the picture. Now finally here on the graph below, graph g of x equals 2 cosine x on the domain 0 to 2 pi. Rescale your x-axis. Oh, it's a hint here. Rescale your x-axis so that 2 squares are equivalent to pi over 2 units. All right, so for the x-axis, every 2 squares, this is going to be pi over 2. This will be another pi over 2, so 2 pi over 2. That's pi. This will be 3 pi over 2, because we've gone 3 times in that direction. And then this will be another pi over 2, so that would be 4 pi over 2. 4 divided by 2 is 2 pi. And we know that we want to graph it on the domain from 0 to 2 pi, so that will be from 0 to 2 pi. All right, now our cosine graph here has an amplitude of 2, and cosine starts off at the maximum. So we're going to start at 2 here, and we're going to go down to negative 2 eventually. So here, all of the important things happen at these key values. So we're at the maximum. Then when we hit the x-axis, well, this is hard to draw. I hate cosine. We hit the x-axis, that's going to be at pi over 2. To get to our minimum, that's going to be down here at pi. We get back up to the x-axis here, and then we hit our, whoa, too high. We go back up to our maximum here at 2 pi. Now I realize that I can't count. This is 1, 2, 3. So let me redo that. All right, so this was -2. So now I think I've got it, so that it's symmetrical above the x and y axis. All right, so this was the exact same problem as the last two, except we had the grid, but it was easy to handle the grid because of rescaling it. So try to rescale these if it helps you. Make sure that you're labeling all of your key values on the x-axis. Make sure that for cosine it's starting at the maximum. Make sure that you're being a little careful with these so you don't make mistakes like the one I made. All right, guys, I hope this helped. Please make sure to complete the remaining problems and send in your pictures. Hope that all is well, and talk to you soon.